Hello, pre-calculus students. I wanted to take the time to make a video lecture on the remaining part of week one, that is the section 1.5, which covers solving of equations. We don't have a formal lecture today, but I wanted to go ahead and get the information out to you so that you can go ahead and complete your homework and quiz number one. So what I'd like to do now is go ahead and share my screen. Now, from the last class, we looked at several examples of theorems that we're going to be using. Namely, we had the zero product law, we had the square root property, and also the quadratic formula. Now, I wanted to go ahead and show you about the quadratic formula, reminding you about completing the square. So all of these theorems are very useful. That is, we would know that A, B, and C are real numbers with A non-zero. Then AX squared plus BX plus C equals 0 if and only if X equals, and this is the famous formula that you know from Algebra 2 and college algebra, the opposite of B plus or minus the square root of B squared minus 4AC. Let me get a little bit more room on my radical, divided by 2a. Now, often you might see problems that say solve for real solutions or solve the quadratic, whatever the case may be, and occasionally it may require you to complete the square. Now, completing the square is an important technique that we need to know how to do, but when it comes to solving equations, usually it's easiest to either factor or to go ahead and utilize the quadratic formula. So when I ask you to solve an equation, you can certainly use whatever method that is most convenient to you. So what we want to do is actually start with this side and show that this is the case. So we want to look at the completing square technique so you can use that more so in this class and also in your future calculus classes. So what we want to do is, here's a famous little, what do we call these, acronym log. Without loss of generality, we will suppose, that is, A is non-zero, so let's just go ahead and suppose that it is positive. And if it were negative, we could multiply by -1, so that won't be an issue for us. Now what we want to do is to complete the square. So we start with this equation here. So we have A x squared plus bx equals a -c. So we just transpose the c to the right-hand side. And now to complete the square, again, there are many ways to do this, and the way I order things is not unique, so don't worry that you may change a little from this. To complete the square, we need what we call the monic polynomial. So the coefficient of x squared needs to be 1. So we have x squared plus b over a. To compensate for factoring the a, we need the division by a here. And then what we're going to do is we're going to actually complete the square. Now, when we complete the square, we do as you've done in your previous classes. You take half of this coefficient and square it. So that means we will get b squared plus 4a squared. Now, of course, if we add a number, we have to subtract the same number to preserve the equation. Now, this is why we did our factoring formulas in the previous lecture. When we look at this, this does complete the square, so to speak. this is now a perfect square. So when we think about the identities that we used in the previous lecture, this is one of them. So now what do we get? This is A times X plus B over 2A, quantity squared, minus B squared divided by 4A squared equals the additive inverse of C. So again, when we think about the perfect square, just as a reminder, we had the formula A squared plus 2AB plus B squared equals A plus B squared. So when we look over here, we see that our A is X in this particular case, and that the B actually in this particular case is the B over 2A. So you could go ahead and say, well, A equals X, B is equal to lowercase b over 2A, and of course, lowercase a also. So when you actually substitute here, we get the X squared, we get the 2 times the B over 2AX, which gives us B over AX. And then of course, when we square this, we get this term. So this mimics the identity that we have used before. Again, we always want to try to recognize patterns because these patterns are what allow us to move a problem forward. Now we're good to go. Let's go ahead and multiply by A. So we get A times X plus B over 2A quantity squared. And now when we multiply by A here, that absorbs one of these A's. So we get minus B squared over 4A. And this equals the additive inverse of C. So now it looks like we're going to be able to use the square root property. So what we want to do is go ahead and transpose this term. So A times X plus B over 2A equals B squared divided by 4A minus C. Now this is starting to look very familiar, and let me not forget my square here. One good thing about math is it really does self-correct you. I mean, as you work through, just let the math tell you what to do. Now, right here, common denominator, let's go ahead and do that. So it's going to be a 4A. So we get the B squared, and then of course we multiply the C times the 4A. So we get minus 4AC. So now, in order to use the square root property, we have to divide by A. So we get X plus B over 2A quantity squared equals B squared minus 4AC divided by 4A squared. Now, again, we have something squared equals a real expression. So equivalently, by the square root property, we have X plus B over 2A equals plus or minus the square root of B squared minus 4AC divided by 4A squared. Now, of course, the B squared minus 4AC, we really don't know what that is in terms of its squaredness, so to speak, but 4A squared is a perfect square. The square root of A squared is the absolute value of A, but remember we've supposed that A is positive. So this can reduce to plus or minus the square root of driver support. You know, get all this malware that tells you you need to add things, always a nuisance. So plus or minus B squared minus 4AC divided by 2A. And now we're good. Well, all we have to do is subtract B minus 2A from both sides and we have the formula. And of course, it has the same denominator as this, so we can join it as one fraction. So we get the opposite of b plus or minus the square root of b squared minus 4ac all divided by 2a. So now what we see when we actually do these types of problems, and I'm sorry, let me move that up just a little bit so you can see it. The formula here, again, when we think about this, if we're solving an equation by completing the square that's quadratic, then we think that that's pretty much repeating this process. But there will be times when you need to complete the square like we've done right here to work a problem. You won't have to go all the way down here, but the technique of completing the square is important. It's just that if you actually go through this process every time to solve a quadratic, that's not always necessary. But the technique that I've done here, you will need again in this course and also in calculus. So the technique of taking a trinomial and completing the square is extremely useful, and you will find that to be the case as you continue your math classes. So I wanted you to see that particular calculation with completing the square so you can re-believe the quadratic formula. Now, let's just go ahead and do some examples where we may or may not need the quadratic formula. So here's some additional problems from your web assign. So here's an example. So what the problem says is to solve for real solutions. Now, as we work into the course, we will say more about imaginary solutions in the theory of equations, but for right now, we're just focusing on real solutions. That is, if we have a quadratic, the discriminant would be either 0 or positive. So we have the following equation: 24 over x minus 27 divided by x minus 2 plus 2 equals 0. Now, these kinds of equations should remind you of what you did in college algebra, maybe algebra 2 when you were in high school, where what you want to do is to rewrite this equation with the common denominator, that is, clear the denominators, and then search for values of x that would make the numerator, so to speak, 0. So if this particular equation has a solution, that technique will actually find the actual real solutions if they exist. So again, we note that x equals 0 and x equal 2 could never be solutions because this would make the equation undefined. So we would basically need to check to see whatever solutions we would determine would not correspond with those real numbers. So at the outset, we can already just say, as I've just previously said, that x is not 2, or x is not 0, and x is not 2. So we always remind ourselves of the prohibited number, so to speak. So now first we see what's the least common denominator. Well, this is just a 1 here under the 2, but we have an x minus 2 and an x. So we need the factor of x and x minus 2. So if we want to clear denominators, we can multiply through by this polynomial. Again, we'll just use a figurative type work where we multiply and let the factors absorb without having to do a lot of additional work. So I'll just say times x minus 2. Now, of course, we have the 0 here, so that's still 0, but really we're multiplying both sides by this polynomial or by this expression. And so again, what we want to do is just notice that when we multiply 20 over x by x times x minus 2, the x is absorbed, and we're left with 20 times x minus 2. So that's very simple. And now when we look at the expression negative 27 divided by x minus 2, the x minus 2 is absorbed, and we're left with 27 times x. So this is more of a visual process to cut down on the amount of work. And now the 2, there's nothing to absorb anything. So we have plus 2. And of course, this is just x squared minus 2x if we multiply that. And of course, the right-hand side is 0. Now, the reason you leave this factored here is so it's very easy to visually absorb the common factors. But when I get here, I know I'm going to have to multiply that out. So I'll go ahead and do it. Now let's go ahead and multiply, and then we'll collect terms. So we have 20x minus 40 minus 27x plus 2x squared minus 4x equals 0. So you're seeing that we're generating a quadratic equation from this original equation. So if we combine terms, we have a 2x squared. So that takes care of that. And then we have some x terms. So the 20 and the negative 27, that'll give us a negative 7 coefficient. And with a negative 4, gives us a negative 11 coefficient for the x. So we take care of those. Just a little check to remind us that we've already added those terms. And then, of course, the last number is the minus 40, which is the constant term. So what we see is we have an equivalent equation for the original equation, which is this quadratic equation. So again, the algebra that we do is to hopefully produce an equation that we understand. And we understand quadratics. So now what we can do is here is we can try the discriminant, or we can just try AC to see if it factors. So let's practice. So first, AC will be 2 times a negative 40. Now, you might be saying, since we have the quadratic formula, we could go ahead and look at b squared minus 4ac, and if that's a perfect square, then we know it factors. So now you have 2 ways to figure out if you have rational zeros. But it's always good to review AC method. Now, of course, when we add these, we don't get negative 11, but we can look at this negative 40 and factor it. So this will be 2. We could say a negative 8 times a 5. Now, of course, the 8 has other factors, a 2, 3 copies of 2. But when we look at this, we see that there might be something that will be of assistance to us. The 2 times the 8 will give us a 16. And if we put the negative with that, the 5 plus the negative 16 will give us a negative 11. So this appears to factor very nicely. We get a Z and a W. So this is negative 16 times 5. Now this is what I was talking about before. At this point, you can use whatever technique you like to solve the quadratic. You could go the quadratic formula route. You could try the AC method. It's completely up to you. So there's nothing that says you have to solve this equation by any particular method. So now, equivalently, we have 2x squared minus 16x plus 5x minus 40 equals 0. So now we do the factoring by grouping, which we like. So now we've got a 2x in both of these terms, 2x times x minus 8 plus, and now we got a 5 in both of these terms, so 5 times x minus 8. Now equivalently here, we see that the x minus 8 multiplies 2x and 5, so we can use the distributive law. So 2x plus 5 times x minus 8 equals 0. So now, using another theorem that I spoke about at the beginning, the zero product, so that means we have a product of 2 real expressions equal to 0, so we can set each of the factors equal to 0. Now, sometimes you can do this very quickly. You can do it in your head and not worry too much, but it's always good to write everything down to make sure that we've covered everything. So now we see we've got here 2x equals -5, divide by 2, x equals -5 halves, or in the second equation, we just have x equals 8. Now, when we look at what was not allowed, neither of these correspond with that. So this gives us a solution set of -5 halves and 8. Now, of course, remember in WebAssign, all responses are to be exact. And if they ask for formatting, you always have to look to see how they want you to type the actual response. Do they want you to separate by commas? Are they going to say x equal and have a box where you separate the actual zeros by commas? Be sure to follow the formatting directions. And if there is no allusion or no direction to approximation, then you always give an exact response, always. That's what WebAssign does. But as far as good general rule for mathematics, the exact response should be something you should be expected to do and know about. Now, let's look at another example. One thing that we can do when it comes to solving equations is to deal with radicals. And again, you did some of this in your previous class. And so in this particular section in our pre-cal class, we just want to highlight some of the things that you've actually done. So this would be a radical equation. So here we have the square root of 3x plus 1 equals 2 plus the square root of x plus 1. Now, these are square roots, but it doesn't matter. We could have cube roots, even nth roots, whatever. The idea is that in order to get rid of a square root, we square. So the process here could be trial and error. That is, you can just try values of x and maybe you'll get lucky and find a solution. But what we want to do is similar to the last, is produce a maybe simpler equation that we can solve, and then see if any of the results that we actually get actually solve the original equation. So what we're going to do is a similar technique. So basically, we will square to eliminate the square root. Square to eliminate the square root. Now, of course, if we had cube roots, we would cube. So we basically, again, when there's no index here, we assume it to be 2. Of course, if there were a 3 there, that would be a cube root. So these are things you know, but may again, just be something that's a little bit rusty at this point. So notice we have a square root here that's isolated, so we can go ahead and square. Now, you don't always have to write out the squaring process, but when you're reviewing, it's good to write down all of the steps. You can always leave out steps once your level of comfort increases. So when we square the square root, we eliminate the radical, so to speak. And now we get to use our binomial identity. We square 2, we get a 4. Then we multiply 2 in the radical and hit it with a 2. So that will be 4 times the square root of x plus 1. And then if we square the radical here, we are just left with the argument or the radicand. So again, the squaring of the binomial identity that we reviewed in the previous lecture we're using, and that's very convenient, very, very convenient. So now what we want to do is collect some terms. So we have 3x plus 1, and here we've got a 5. 4 plus 1 is 5, plus x plus 4 times the square root of x plus 1. Now again, we want to isolate the term with the radical, so let's remove everything to one side. Now again, it doesn't matter, completely your choice. So again, if we subtract x from 3x, we get 2x. And if we subtract 5 from 1, we get a -4. And this gives us 4 times the square root of x plus 1. on the right-hand side. Now, of course, we have extra stuff here. We've got a 2 in everything, which isn't going to affect the solution. So let's divide through by 2, just because the numbers being smaller make the problem easier. So x minus 2 equals 2 times the square root of x plus 1. So we've simplified the problem down to 1 radical. So what we're going to do is square again. Now, one thing about squaring is that there are possibilities of introducing what we call extraneous zeros. So when we get values of x, we want to make sure that they actually solve the original. So again, just a word to the wise, don't do a happy dance with the values of x until you've made sure that they actually work in the original equation. So we square again. So now we can now square, know that we have to do this. So I'll go ahead and write this out, but you could have left that step out. You can just visually square, but just go ahead and put down all the steps for now. So here when we square the binomial, x squared, and then we have a minus 2x hit with a 2, so that's a minus 4x plus a 4, the perfect square. And now we square the 2, we get the 4, and then of course squaring the radical gives us x plus 1. So now we have x squared minus 4x plus 4 equals 4x plus 4. Well, this is certainly a lot easier than what we started with. So now we see the 4's absorbed, and we can subtract the 4x from both sides to give us x squared minus 8x equals 0. Well, we really like quadratic equations that have no constant term. So equivalently, we have x times x minus 8 equals 0. Now again, we have zero product, so we can look at this and say, all right, zero product theorem says we can set each of these factors to 0. So x equals 0, or x minus 8 equals 0. And this will just say that x equals 8. So with this particular example, what we see is we have 2 candidates, so to speak. So first, we just want to check our original equation, which is this. So we can go over here and do a check. And this can be visual for you, just a quick check. So let's start with x equals 0. Now, when we replace x with 0, we get a 0 plus a 1. So that's the square root of 1, question mark, 2 plus square root 1. Well, that clearly doesn't work. I mean, 1 doesn't equal 3, so that's no good. So we discard x equals 0. The idea is that our process generated a value for x that does not solve the original. So that's what we call extraneous. I guess you can give a fancy name to everything, but it won't work. So now x equals 8, we can check when we replace 8 here, we get a 24 plus a 1, so that's the square root of 25, question mark. Now we have a 2 plus, now we add 8, we get square root of 9. But this does work because this is 5 and this is 2 plus 3. So that's a check. So now we see that the solution set is simply 8. Now, this is not a hard problem. It's just a longer problem. What we find in doing mathematics is that the procedure may be very simple in the sense that the techniques we're using, we understand. But we have to be very careful that whatever we actually produce actually is a solution to the given equation. So again, this is a good example just to remind you of the techniques that you learned in college algebra. Okay? Now, there's a theorem when on the last lecture, I listed some actual types of problems that we'd be doing. And with the equalities, we want to say a little bit about absolute value. So here's a theorem here. We're going to have absolute values tied up with inequalities, and we'll say more about that at the next lecture. But if we suppose that C is a positive number, so we have some positive number C, then, and this is easy to remember, then the absolute value of X equals C has an equivalent interpretation. That is, if the absolute value of X equals C, then X equals C, or X equals the additive inverse of C. So you can look at this and just basically think of the definition of absolute value. The absolute value of X here is always non-negative. So by definition, the absolute value of X is always non-negative. So if we take the absolute value of a real number that's less than 0, it becomes positive. And so that's why when we look at this particular theorem, that not only do we include X equals C, but we include X equals the additive inverse of C. Just remember that the function absolute value of X can be defined in pieces. That is, the absolute value of X is X when X is 0 or positive. That is, if we think about this, a non-negative input is unchanged, but we get the additive inverse of X when the input, in this case, which is X, is less than 0. So by definition, we get this result here. And so again, this is a very straightforward result, but very useful. It's like the square root property. You don't forget the minus. Plus and minus square root. Here we have like a plus and minus, so it's very similar. So here's a simple example of this. So say we have the following, that is, solve for real solutions. Now, of course, this is not very difficult, but what's difficult is when you don't review something like this and then you see it on a test and you blank. So it's good just to go back through these things. So the absolute value of 2x plus 5, I'll just do a simple example here, equals 10. Now just remember that in order to use this theorem, you basically have to see that you have the hypothesis here. So now what we see, and this is an easy one, we actually have the absolute value of some argument isolated, which is what we have here. And then we have the C, a positive real number right here. So when we look at this, we see that the theorem directly applies to this. So we can say apply theorem. Just remember, in order to apply the theorem, we need to make sure that the hypotheses are satisfied. So if we had to redistribute, isolate things, then we would need to do that first. So now by the theorem, we just follow what we call the recipe. So we have X equals C. So that says 2X plus 5 equals 10. So X is replaced with 2X plus 5 and C is replaced with 10, or 2X plus 5 is equal to the additive inverse of C. So again, we're just mimicking this equation and this equation. So this says 2x, if we subtract 5 from 10 is 5. So x equals 5 halves. Or we have 2x, subtract 5 equals negative 15. So x equals negative 15 over 2. So again, we extend the solution, so to speak. So now we have a 5 halves and a negative 15 halves. Now, of course, with this theorem, we're not introducing extraneous solutions. So if we do our work correctly, then we're fine. you can always check your solutions, but maybe to save some time, if you know that the procedure does not produce extraneous ones, then just recheck your work and move forward with that. Don't feel like you have to check everything for validity. We would only really need to worry about checking things when we had the probability or the possibility, excuse me, of creating a solution that would not work. Okay, so now let's look at some quadratic equations. For instance, I started off with the, and we'll do a fresh paper. I started off with the quadratic formula by completing the square. And so now let's just see. Let's try a quadratic equation where maybe we can't factor, that we will have to use our theorem. So here's an example. Quadratic equations are everywhere. Quadratic form, we need to understand quadratic equations. So I'll say solve for real solutions. Now we can also say solve in R. We could say solve in the real numbers. This means the same, using our script R for like solving real numbers. Or if we wanted to include imaginary, we could just say solve for all solutions, or solve in C. So we have 4x squared minus 16x plus 13 equals 0. Now, when you look at that, you see that's a standard quadratic equation. So let's just go ahead and decide we're going to use the quadratic formula this time just to get practice. So first we say A is 4, B is negative 16, and C is 13. So the idea here is if we're going to use the quadratic formula, the first thing we're always going to compute is the discriminant. And I want to say this again, and I'll repeat myself. When you use the quadratic formula, compute the discriminant first. Do not substitute all the numbers into the formula and then try to manipulate the arithmetic. That is the worst way to do it, in the sense that it is too difficult to keep track of everything. Go ahead and get that discriminant, double, triple check it, make sure that you have the type of solution set in your mind before you move forward. This will always be a better way to do it. So now we have negative 16 quantity squared minus 4 times a 13. Now, a lot of times when it comes to doing algebra, you factor, but when you look at numbers, you never think about factoring, but they're the same thing. So notice here we have a 16 and we have a 16 here that's going to go away, but I'm just going to go ahead and now say this is 16 squared because the negative absorbs, minus 16 times 13. So what I've done is I've dressed this up a little bit so you can see that we have a common factor of 16 in both of these terms. So we're going to factor that. So that's 16 times 16 minus 13, just to keep the numbers more manageable. So this is just 16 times a positive 3, and that's positive. So this means two distinct real solutions. So the idea here, it doesn't matter when we do this. I can always move my picture around to get it out of the way. The technology is really amazing these days. I think we're in awe of it. So two distinct real solutions. Now, the idea here is we can move forward knowing that we've got a perfect square here. So when we take the square root of this, we're just going to get 4 times the square root of 3. So that's going to make our procedure much easier. So this implies that x equals the opposite of b, that is 16, plus or minus. Now we take the square root of this, So I'll go ahead and write it out. We have 16 times 3 divided by 2a, 2 times 4. So now we have 16 plus or minus. Now the square root of 16 is 4. We have 4 root 3 divided by 2 times 4. Now you can leave this as one fraction, or you can break it up. It doesn't matter. So we have 16, that's 8 divided by 8, plus or minus 4 root 3. And I'll leave it factored for this one so we can see the common factor of 4. So this will give us 2 plus or minus. Now here we notice that the 4 is absorbed, plus or minus square root 3 over 2. Now, one thing you can see here, it wouldn't matter if we kept a common denominator of 2, and of course that would be a 4, but just personal choice here. So now notice that this was really a good idea to utilize the quadratic formula, because what we see here, the discriminant was not a perfect square. So if we had tried Professor Ron's AC limit, it would not have worked. We would have been unable to get a z and a w to factor. So this now says, equivalently, that we have solutions 2 plus square root 3 over 2, and we have 2 minus square root 3 over 2. Now, here's another thing that's important. When it comes to, again, solutions, no approximations, you type the solution exactly. So when you hit the response box, then you're going to need to use the little palette that gives you the square root symbol. And then you place the 3 as the argument. Everything exact. Whatever sign may say, type the largest 0 first. Or they may just say, type the solution separated by a comma. Always take time to check out the formatting directions. It'll save you a lot of time. We don't like to follow the formatting directions. We finish the problem. We just want to type something in and move on. We know it's right, but the software has to analyze what you've typed. And you must tell it what you mean exactly. And if they request certain types of formatting, then all you have to do is make sure that you abide by that. It's not unreasonable. For instance, when you're working with individuals or you're doing things online or anything that you do, there are always certain directions that make the process of analyzing easier for someone else. So just keep that in mind, that formatting is not something that's a complete waste of time. Okay, now what I want to do is look at some other examples. One example that you'll see in your WebAssign is a quadratic form. Now, we understand the quadratic equation, and we know that the square root property is basically just a special case of that. Now, what you'll see in your WebAssign problem is a quadratic form instance that may be a little bit difficult the first time you do it. I've actually done this in the SmartPen videos. So it always makes a good example for a lecture problem. So again, solve for real solutions. So here's what we have. We have 4x to the negative 4 minus 16x to the negative 2 plus 4 equals 0. Now, when you look at this, you're thinking, well, it kind of looks quadratic, but I've got a constant term, but I don't have x and I don't have x squared. But the idea is that we do have quadratic in another expression, and it doesn't usually take much time to figure that out. We just want to write the expression in a way that will make solving the equation a little bit easier. But the first thing that I'll notice here, and that you should notice too, is that we have a 4 in each of these terms that's just taking up space. So first, what we can do is divide by 4. So that's x to the negative 4 minus 4x to the negative 2 plus 1 equals 0. No need to carry around additional numbers. When all of the terms have common factors in an equation, retire them, because the smaller numbers make the process easier. Now, one thing you'll notice, if you square x to the negative 2, you get x to the negative 4. So that is quadratic form. So one thing that might make this solving process a little bit easier is maybe to write the expression here in this equation as fractions. So for instance, we can do this. We can just write 1 over x squared for x to the negative 4 minus 1 over x squared plus 1 equals 0. And that might make it look a little bit more obvious that this now is quadratic in the expression 1 over x squared. The negative powers are not a problem, and there's nothing wrong with that, but it might make it a little bit easier to analyze when you start solving things if it's written this way. And that's, again, is just a personal choice. Now, again, this is quadratic. We have a equals 1. That is, the coefficient here is 1. B equals negative 4. And C equals 1. So again, quadratic, just like the previous problem, but quadratic in a different term. So now we look at the discriminant first, because we want to keep everything nice and efficient. So we have b squared, so that's negative 4 quantity squared, minus 4 times 1 times 1. Well, that's the easiest in the world. That's just 16 minus 4, which is 12. Again, that's a positive number. So at least for the first part, we have distinct real solutions. But notice here, we got this fourth power going on. So really, we're expecting intuitively that we're going to get 4 solutions. So now we're good to go. So now instead of x, we have 1 over x squared equals the opposite of b, which is 4, plus or minus. And now we can take the square root of 12. Just remember that 12 equals 4 times 3. So now we can consolidate. This will be 2 times the square root of 3. Again, the square root of 4 is 2. We get 2. The root 3 stays behind, or the 3 stays behind under the radical, divided by 2 times a, 2 times 1, which is 2. Divide everything by 2. 2 plus or minus the square root of 3. Now, this is good because the next step will just be the square root property. But what does this say? I'll do the equivalent there. But first, this will say, if we reciprocate both sides, x squared equals 1 divided by 2 plus or minus square root 3. So now let's look at each of these solutions, or each of these equations, with the different numbers here. So we'll do the plus. So we have x squared equals 1 over 2 plus square root 3. Now there's absolutely nothing wrong with this. We can take the square root of this, but one thing you've noticed is that if that's the case, can we go ahead and rationalize this and maybe simplify it a little bit? Just a personal choice. So again, we can do the conjugate technique. Again, you don't have to do this. It doesn't make the other solution incorrect, but this is just a nice little trick. Notice here, downstairs, we just get 4 minus 3 because this is a difference of 2 squares. So that's just a 1. So this gives us 2 minus root 3. Not surprising. Or x squared equals 1 over 2 minus the radical 3. So let's go ahead and do the same thing. Let's rationalize it. 2 plus root 3. This is just a little extra for practice. You don't have to do it. Now again, we have the difference of 2 squares in the denominator, just like before, 4 minus 3, which is 1. So we get 2 plus square root 3. So this is an additional part just to make the solutions look a little simpler, but not required. Now, square root property, square root property. So x equals plus or minus the square root of 2 minus square root 3. The square root property is very useful. Or x equals plus or minus the square root of 2 plus square root 3. Now, what we see with this particular application of the quadratic formula is that we do indeed produce 4 solutions. Because when we look at this, this is basically 1 over x to the 4th power. So you're thinking, okay, it's not really a polynomial, but it is quadratic in 1 over x squared. So again, you look at the original problem, the original equation, and intuitively you think, well, possibly 4 solutions. So again, you know, we're utilizing the fact that we understand the quadratic equation and quadratic formula, and we see that we have an equation that has what we call quadratic form. Quadratic form. And how do we get that form? Well, it's quadratic in this particular expression. So again, what's important to see here is that our theory for the quadratic equation can always be applied to an equation in quadratic form. And so now we can simply list the actual solutions. So we have the square root of 2 minus square root 3, the negative or additive inverse of the square root of 2 minus square root 3. And then for this side, we have the square root of 2 plus square root 3. And then we have the negative or additive inverse of 2 plus the square root of 3. Now, the thing is, these solutions look very similar. Here we have the minus square root 3 under the radical, plus and minus. And here we have the plus square root 3 under the radical, plus and minus. And again, these are all real solutions. So what we see about this particular example here is that even though the equation looks very difficult, the way the WebAssign sets this up and the way Dr. Stewart sets up his sections is to supply you with problems that can be solved with the given theory in the section. Or maybe you can apply something from the section and from previous sections to actually solve this. So I want you to be aware that even though this takes more time, any equation that would fit quadratic form can be solved with the same type of technique. We may have found that maybe we had some imaginary solutions or whatever, but what we found in this problem is that all the solutions were actually real. Now, so what I want you to do is I want you to finish your WebAssign problems for all the sections. That is, remember, we have 1.3, 1.4, and this concludes 1.5. So these techniques, though again, a little bit dry, are very, very important. So as we work into next week, we're going to talk about some applied problems. That is the standard time, rate, distance, fraction of work, and mixture problems, again, that you did in your college algebra course. And then we're going to talk about some basic inequalities, how we actually work with inequalities and how does that impact absolute value. And then review topics for the definition of a function. When we take calculus, we need to understand algebra and how it impacts algebraic functions and also transcendental functions, the logarithmic functions, exponential functions, and also the trigonometric functions. And the main tool that we use to do all of that analysis is the function. Because when you get to calculus, you talk about limits of functions, derivatives of functions, Riemann sums of functions, integrals of functions. So that really, when we think about it, the abstraction that has served us really quite well in mathematics is that of the function. And so whatever time we spend on functional analysis is actually very important. So this will help us to set up some of the algebraic rules and the algebraic manipulations that we need to be able to do to solve these types of problems. So what we'll do now is we're set up for next week. So remember your homework, first set, 1.3, 1.4, 1.5, and then also quiz number 1. So I hope this has been helpful with some techniques for solving quadratic equations. I'll go ahead and stop the share from my screen. And I wish you well as you continue with your study. Do take advantage of the Smart Pen videos. There are plenty of those. And then of course there are practice tests from previous classes that give you additional problems with solutions included. Just remember that when it comes to algebra, that techniques that you already utilize that are legitimate and work for you and that are correct, then continue to do that. But what we want to do is make our processes efficient, but not necessarily so quick that we don't have good conclusions. So we want to make sure that as we work our algebra, that we're actually making good mathematical choices. Okay, everybody have a great day, and we'll see you next week.